Hi, this is Terry Kushma back here at Penn State University, and we're going to continue our discussion in materials and nanotechnology. This is an introduction to nanoparticles, the synthesis and applications. This is part two in our series, and specifically what we're going to discuss today is pyrolysis. So here's our outline. So we've covered the things. If you're joining part two, we've already covered the material that's above pyrolysis in this outline. But today what I'd like to do is focus on pyrolysis and provide some details for this particular process because in our list of processes, I guess this is where the majority of nanoparticles that are manufactured in the world come from. So this particular process makes the most nanoparticles, and for example, this is where we would get nanoparticles that provide the backbone for paint. This is for the nanoparticles that would be for rubber, like car tires, etc. So this is an area where we produce a tremendous volume of nanoparticles for society. So I'd like to certainly spend some time on this. So pyrolysis is a popular method for creating nanoparticles, especially oxides. So generally a precursor, either a liquid or gas, is forced through an orifice at high pressure, and the energy that we would generally use at this point is heat, so it's burned at that point. So the resultant ash or byproduct is collected to recover the nanoparticles, and large volumes of this gas leads to a high rate of material synthesis. And again, this is necessary because if we would look at these typical products that are made with nanoparticles that come from the pyrolysis process, so certainly the carbon black that is used in tires and the carbon black that's used in inks, and certainly things that are expensive in life generally are, car tires. I think I put new tires on my truck and it was close to $1,000, $800 or $900 for the tires on my truck. And ink for like inkjet printers, for Hewlett-Packard inkjet printers, certainly very expensive. Commodities like paint, the backbone of that is titanium dioxide, again created through pyrolysis. And interestingly, the pyrolysis method can be changed or enhanced, that we make certain formations of Si or titanium dioxide, and some of those would be like UV protectants, and others would act mechanically to provide a backbone for the polymer, for the polymer matrix for paint. And expensive things in life. My wife buys makeup. Oh my, it costs a lot of money. And so there's all kind of metal, nanoparticles, etc. In makeup. So that's another portion, certainly optical fibers. And one of the things that's used quite a bit worldwide in the food industry is materials like silicon dioxide for a flowing aid. So these are often incorporated into materials like chocolate, and they act like mini ball bearings in there to help the chocolate during the manufacturing process fill up a casting for a candy bar or something like that. They are also used SiO2 for as like an anti-caking agent in materials like certainly as pharmaceuticals as shown here, or other products that we'd buy like orange juice, etc. And interestingly, the FDA, the Food and Drug Administration in the United States, considers SiO2 like air. It really doesn't even have to be listed. I think it's not mandatory that it's listed on consumer products. So that's very interesting. And again, pyrolysis is a mover and a doer for all these common materials that we see here. So interestingly, this is made in quite the commodity. So I should have a reference on here. This is actually an old slide, so it's dated. But we make carbon black, for car tires by the millions of tons, and titanium dioxide by the millions of tons, and silicon dioxide by the millions of tons. And again, I think the slide's dated, that should be even more than this. So there's billions and billions of dollars, certainly through the initial manufacturing of these materials through pyrolysis. So historically, if we would look, past World War II, World War II naturally ended in 1945. After that, the German companies were trying to come back online. So Degussa here in Frankfurt, what they advertised in their, magazines or whatever, periodicals, that they were making millimicron, 4 to 20 millimicron SiO2 for different applications, like the paint industry and the lacquer industry as a binder. So certainly these are still a driver. This company's still a driver in commodities. So they make carbon black, and they were certainly a driver to take the byproduct of the oil or gas industry and use that carbon black in a burning process to make rubber products. So again, like in World War II, that was a driving force to get synthetic rubbers, etc. Because they made things like polyisoprene instead of the native rubber plant, that was indigenous to the I guess the theater where the Japanese were occupied. So for the U.S., it was important for us to even have that stuff. And just as a notation here, this gentleman here down below in this reference, he's really probably one of the better people in nanoparticles, and certainly a leader in research in nanoparticles. So he established a lot of these processes and brought this stuff online within the last couple decades. So he's really instrumental to, and his students are instrumental to research in this area. So this is a school of showing what they did, like Degussa. They would take the byproduct of like gas, burn it in burners, and do a collection of that material, and this would be the carbon black. So this was a I don't know, this is an efficient use of a byproduct that they would make carbon black. And interestingly, the burners on here are scaled to be rather small. So the flames generally on a pyrolysis system are measured in a few centimeters. So typically these would be like a lighter or something like that. So you'd envision that these flames would be rather large. There's certainly a large amount of flames, but each individual flame is small, and there's a number of these flames, and we're going to see the rationale for that later in the presentation. So this is the flame pyrolysis method, basically a schematic, and I think it shows a lot. So the scale on here, I should probably have a scale on here, that is a few inches, a number of centimeters, this flame. And basically what happens in this, we're going to take our precursor gases shown here at the bottom, and we're going to mix that through our burner network, and then we're actually going to light that up. And within this the burn time, what we have is we actually have the droplets evaporate and be chemically active. They nucleate and then coagulate into very small, dense particles, because they have a lot of energy at that point. Later in the flame, when it goes towards the top of the flame, we would get what we would call more agglomeration at that point, where the particles are loosely linked together. So the more durable products come earlier in the flame. So here at the end of the flame, this is where we would get multiple particles put together, and they would tend to be weak. And you would tend to have a wider Gaussian distribution of particle sizes at this point. So probably something that we're going to get to in the presentation, we're going to look at how we would truncate the flame into here, because really this, and how we would control the flame, this middle area is probably where we would get the most robust nanoparticles and the particles with the smallest Gaussian distribution, and certainly that's desirable. Interestingly, shown even on this drawing, what we're going to do to change that is the order or the sequence of this burner. So we can change certainly the mass flow through here, the temperature, etc. But one of the things that is going to be used to control these particle sizes is actually the arrangement and order of that mixture, which is very, very interesting. So this is a typical system in pyrolysis. So what we're going to do is we're going to have our source of our material over here on the right hand side going towards the left. We're going to introduce our materials, put it into a burner, and then from that point we're going to have some kind of collecting or filtering network that goes through some kind of rough vacuum system. there on the left so that we could, again, collect this material and use this for our products. And again, this is done by the ton. So this is a fairly macro industrial application that we need to provide the materials for, like car tires and paint across the world. So pyrolysis, I guess a discussion here is the difference between an aggregate and an agglomerate. So an aggregate is basically an assemblage of particles that are rigidly joined together by chemical or sintering forces. So an aggregate, I always think about, at least in English in the US, we would refer to like stones and like the rocks you would have in a driveway for you know, cars to travel over. We would call those aggregates, something that is very durable and strong. And an agglomerate is a loosely coherent assembly of particles or aggregates together. So these would be linked together rather loosely, and they tend to be larger and per se brittle. And at that point, when we generally discuss agglomerates, they would have a wide range of sizes because we get this loose coupling together. So for the most part, as a word, the word aggregate is probably more desirable. Excuse me. So agglomerate formation sequences is what we're doing. So in a spray, we form these monomers, and then we form transient hard agglomerates, and then into spherical particles. And then further in our flame, what we're going to do is we'll have enough energy at that point to further form hard agglomerates. And again, this is probably the area right here that is the most desirable because these are robust and a small Gaussian distribution of sizes. Then further in the flame, as we go along in time, these are going to be softer agglomerates to where the hard agglomerates are going to be loosely connected together. So they could be useful for some applications, but for the most part, as engineering, we probably want to work with things that are you know, rigid for most applications. So the soft agglomerates tend to be less desirable. So hard agglomerates, I guess we could identify those as maybe even aggregates more appropriately. It depends on the terminology. So the degree of the agglomeration or aggregation, it matters. So for agglomerated or highly agglomerated, tightly aggregated materials, we would use these for fillers, catalysts, particles for CMP because they have a nice narrow distribution and they're fairly mechanically robust. And for non-agglomerated materials, we could use those for things that are per se less mechanically intensive, like pigments, composites, and electronics. So this distinction, there's really no you know, hard definition. What is a hard or soft agglomerate? What's an aggregate or agglomerate? But aggregates are generally hard, well defined, and agglomerates, and certainly soft agglomerates, are the opposite of that. They tend to be larger and linked together mechanically with less robust. So this shows us the regions as we look at the resonance time within the flame. So in the first time period here, shown in seconds, so a thousandth of a second, we're going to get these non-agglomerates, and this is basically a chemical stage here where we're initiating the nucleation of this material, and it's nice because we have a lot of energy at this point within the flame. Then later, what we're going to do within the flame at the resonance time between here, shown in the gray, this is where we're going to form the hard aggregates or hard agglomeration, and these are the particles that are the most desirable at this point. Later in the white region, again past the gray region, this is where we're going to get the soft agglomerates. So this is shown again, the link here on the left. We have some pictures that are shown taken off these areas here. So this shows us the importance of that we would probably want to filter or truncate the flame in the area here and shown in the gray, because that's going to give us the particles that are, you know, the assumption is that these are probably the ones that we would want the most because they're certainly mechanically robust. So let's take a look at maybe something that's rather counterintuitive, the effects of oxidant flow on a flame. So again, if we look at flames, and we have a nice scale bar here on the far right drawing, and 5 centimeters is around 2 inches or so. So the average flame is 2, 5, 6 inches, something like that. So it's in a number of inches, and certainly scaled in centimeters. So this would be typical of a burner size, and we would have multiple burners again to get the volume that we need. But it's interesting if we would look at, as we have oxygen in here, the oxygen flow rate, as we go further to the right, we're increasing oxygen flow rate, and actually the flame gets smaller. I would think that the reaction would be greater and the flame would be hotter, but actually sometimes the oxygen itself would be in such a large amount that it would actually act as a diluent. So instead of making the process making the process happen and used as an oxidizer or used in the chemical process, what it's going to do is act to prevent things from happening. It's actually going to act as a diluent because there's too much oxygen within the flame design, the burner design within these burners. So the impact, if we look at oxygen and what it does for us, it aids in certainly the combustion of this process. It certainly provides chemistry in the reaction, and it could also add a tremendous amount of oxygen in there, more than can be used in the combustion process. It'll act as a diluent and it actually cools the flame down, because it doesn't, at an excess amount, it will not be able to participate and have time to participate within the process. So what it's going to do is it's going to cool the flame. It'll make more agglomerates than aggregates, and it's probably potentially bad. And certainly one of these bad points is if you would look at any manufacturing process, a general one, a lot of them use electricity, so that's incorporated into the price of your product is the energy needed, and certainly raw material. So one thing that most companies would say is, I wish I could use less electricity in my process, or I wish I could use less energy in general, and certainly less of a raw material like oxygen, because oxygen is fairly expensive. So let's take a look at the particle size controlled by the oxygen flow. So when we look at the oxygen flow rate in a given standard burn system, of burner design, we can look at the size, and as we increase the oxygen flow rate, actually we hit a peak here at 5 liters per minute, and then as we go beyond that to like 10 liters per minute, actually the size of the particle, because it's now in per se a diluent phase, it's actually going to be smaller. So as we burn more oxygen, as we increase the flow, not burn more oxygen, as we add oxygen to the process, actually our particle is going to get smaller. So certainly if I had, not knowing all the attributes of this process, but if I wanted to have a 60 nanometer particle, I would certainly probably lean to exploring the potential of having it done at around 3 or 4 liters per minute, other than having it to be 6 liters per minute, because this would probably cost 50% less in oxygen, that you have to buy oxygen as a raw material to get the same product. So this is an interesting drawing, and certainly as an engineer, or economically viable engineer, I would explore this region here that I'm using less oxygen to get the same particle size. So again, particle size is controlled by a lot of variables that we're going to explore within this packet. One of them certainly is going to be the flow rate of our oxidizer. So again, let's take a look at, per se, a review of what happens in the particle formation. So we start with our original molecules that we're forming, and this is I certainly can't pronounce that, but this is the chemical matrix that we're taking a look at. And then what we're going to do is form titanium dioxide within the flame. And as we decrease the temperature, go further within the flame, what's going to happen is we're going to form these types of particles. So these particles are going to be the robust ones that we probably desire, and then later these are going to be the loosely coupled ones as we go into the flame. So this is an interesting design here, and maybe I should have some more written commentary, but I wanted to show particle sizes on here, so I didn't want to reduce the picture that much, but this shows the particles. So there's certainly a huge difference in particles and what the particles look like and how they're formed, etc. And these are, in some senses, exactly the same burner. So what we're doing is, as a control in here, we're going to have the same mass flow. So for our CH4, we're going to have the same amount of air. The titanium chloride, the same amount. So that material or mass is fixed throughout these 4 burners. So what we're basically going to do, interestingly, is we would take the burner design and we chemically mix these in a different formation. So we're going to spin these chemicals together, and actually that physical process of allowing this chemical reaction to take place along with the heat is going to produce, interestingly, different particles. So this is certainly an epiphany that we would get different particles using the same amount of materials. So as far as our perspective from manufacturing, this is very, very important, because what we could do is simply reduce the amount of raw materials or conserve energy or conserve cost and be able to get to the same point or the same desirable particle size. And then certainly from that, we could look at particle distribution, you know, what size we're getting, and the rather Gaussian distribution of particle sizes, because often that's important for most applications. So again, like taking a look at the effect of oxygen composition on the morphology. So if we would look at you know, the flame mixing in B versus C, so we're going to assume that, you know, this is one burner type, and this is how we have the arrangement of materials. And again, we're going to keep this experiment that we have the same fixed volume of materials going through the burner, but we actually get this results. And then using the same burner materials, but rearranging the burner configuration, now we get these materials. So again, this is very, very striking, because most, I think it would be intuitive or our first assumption that we would say when we change the chemistry, we certainly are going to get a dramatic impact. But here we can keep chemistry as a fixed commodity and then change burner design. So this opens up the door for us, in some senses, to cheaply design the burner or the arrangement of the burner. And what we're able to do is use our materials more efficiently or cost efficiently. So this is really a huge impact in an industry to be able to do this, or certainly a competitive margin here to be able to use engineering to get the appropriate material at a cost-effective price point. So this shows us probably what we want is flame length controls the particle that we want. So in some senses, maybe a goal that we would want to at least aspire to is we want to take the flame and truncate the flame halfway through or so, and that's going to give us the particles that are going to be the most robust, because the particles that are formed in the latter part of the flame are going to be the ones that are agglomerated and rather mechanically loose. So I guess the goal here, or question or rhetorical question, is how can we simply truncate the flame in the middle to get the best particles, the most robust particles, and then naturally how we're going to control the size when we go back here is how we would do the burner, you know, mixture. So we have a couple things that we're going to do here at one time. Is we want to truncate the flame and then probably control the size. The size of these particles through the burner design or the burner mixture. So that's exactly what we do. We control the burner mixture down here. You know, we're doing this probably empirically. We're going to look at different configurations of mixing the gas together. And then basically what we do, which I thought was novel, we typically have a, you know, maybe a 4 centimeter here of flame, so that, you know, two inches or so a flame in here. And what we're going to do is we simply take a filter. So this is a plate with a hole drilled in it, and we lower that down. And what we're going to do is able to truncate the flame. So in this method, what we're able to do is this region right in here is probably, I imagine, where we're going to get the best most robust particles and the smallest particle distribution. So what we basically do in our manufacturing process, we lower this filter where it's going to truncate the flame, this hole, and then what we're able to do is control the titanium synthesis. So again, this is what people would do to make the powder backbone in paint. So to control paint or the titanium dioxide powder, the quality of those nanoparticles, which is going to be extrapolated to the quality of the paint, this is what we're going to do. And interestingly, that's going to control things like UV properties of the paint, or UV absorbing, so that the paint doesn't fatigue over time. So it's interesting. Here in the U.S., we have places like Lowe's and Home Depot where you would buy paint, and on the paint cans it tells you about this process and the control of nanoparticles to make a better paint. I think that's rather interesting for the public the people to advertise that on the paint cans. I thought that was fairly novel. For an engineer, nothing, but for the population at large, I thought that was interesting. So this shows us the particle size controlled by the nozzle quenching. And again, nozzle quenching is the ability to move this burner nozzle distance. So this is where we're going to have that filter where this is going to lower down this hole, and that's going to truncate our flame at that point. So what we're going to do is we're going to control that distance, and as we control the distance, we're going to control the particle diameter size. And again, when I teach in class, I have a discussion, and when I would look at this graph, one of the things I would see in this graph, I would certainly identify, I mean, you might need a certain particle size, so you need to get that particle size. But to get a particle size of, 20 nanometers, if I look at this one, I see that this is really ugly. Because this has a broad distribution over process parameters. I would probably steer away from something that has such a wide distribution. This might be a process that can be identified as being not really under control. So these have a tighter control range over the amount of oxygen. And again, we're getting the same particle here using less oxygen. So why would we, per se, use more oxygen and get a bigger distribution at this point, or change? So I would change burner design and look for a process that was rather under control. So again, particle size can be controlled by generating electric field across a flame. So basically we can do the same thing. Instead of mechanically truncating the flame, we can treat, which I never knew, we can actually create a high electrical field. So in research, when they're looking at product design and burner design, what they can do is they can mechanically control or electrically control this. Certainly, I don't know if this is scalable to industry because it costs a lot of money to have such strong electromagnets to control the flame. But I thought that was interesting to show this. And again, it shows the same process, that we're getting filtration by controlling the residence time within the pyrolysis process. So again, this shows the same entity that we did mechanically, but now we're showing that we're able to truncate the flame through an high electric field film. So pyrolysis itself, the advantages and disadvantages. Pyrolysis is certainly a high yield method that is able to fulfill the strong demand for nanoproducts across the world. So this is basically the backbone of, rubber, sandpaper, things like that, food, a lot of food products, ink, etc., paint. So this stuff is produced by the millions of tons per year, and it can be customized certainly to produce unique nanoparticles. So we saw we have control variables in the manufacturing method, and again, we can establish these control variables, manipulate them to get to the appropriate particle, and then per se lock those into place to give us a nice distribution of particle sizes. So we can control a distribution of particle sizes. We can also control the morphology, and we can also provide further tightening of the Gaussian distribution of sizes by some filtration and separation processes. So I'd like to end the presentation at this point as just a pointed discussion on pyrolysis because it's so important to manufacturing. The next time what we're going to do is we're going to review some other methodologies such as RF, plasma, thermal decomposition, and the pulsed laser method, and then just look at applications for nanoparticles in general. So I'd like to thank you for your time. If you have any questions, get in touch, and then we'll see you next time. Take care.